So good afternoon. Today I'm going to talk about the log-analytic uncertainty relation. The content of this talk is just reminding you a few things that you probably know about quantum mechanics, talking a bit about the properties of the wave function, connecting it somehow to Cauchy's integral formula and Cramer's Kroning relations, and then giving a specific example regarding the propagating wave packet, and finally reaching to the log-analytic uncertainty relation. Now, all this can be found in this paper over here, phase modulus relation for a reflected particle, which was published some time ago. This is where it all starts. This is the well-known Schrödinger equation. In 1926, the rumor tells us that Schrödinger had a very intensive affair, and he was productive, scientific, and in other ways, and got this equation, and got this paper published in Physical Review. Now, the object which we have to solve for is the wave equation, a wave function, and it has two parts. One is the amplitude and the other is the phase. Now the amplitude has an obvious meaning in terms of the probability density, but what does the phase mean? Well, obviously you can measure a relative phase. You have a superposition of two wave functions, and then you can measure the relative phase in interference experiment, for example. But what about the absolute phase? Does it have any significance? Well, it seems that you can easily modify it by a gauge transformation. So if you just take another phase and you change your vector potential and scalar potential with a gauge transformation, then you get basically the same physical system, but with a different phase. So it seems it doesn't matter that much. So here is the obvious modification of the phase. But let's look at this problem in another way. Let's go even backward in time. This is Cauchy's integral formula from 1831. So we all know we have analytic function in the complex plane. If we have just a point A inside the trajectory gamma, then we can do this integral and recover the value of f at this point A. This is if A is inside. If it's outside, then we obviously get a null. Now, about the same time that Schrödinger got his equation, there was another two people which apparently did not know each about the other. One was Cramer's, the other was Kroning, and they got a relation which was quite important in optics. So let us take another trajectory in the complex plane, and chi here is a complex dielectric function, which is a function of frequency. So we take a complex frequency domain, and if we have this kind of trajectory, then we get a null. Now, of course, we have to say a few things about chi to get some physical result. One, of course, is that chi must be analytic in the upper frequency plane. But the other one is that the response of the system is causal in the time domain. It means that the output depends on past and current inputs, but not on future input. And one can show that in those cases, chi of omega in the frequency domain must vanish on the infinite semicircle. So you don't have any contribution from the infinite semicircle, and you get this integral as a sum of those two contributions, which everything must be equal to 0. Again, this part does not contribute anything. So you get this result, and from this result, and taking the real and imaginary part of chi, you get the well-known Kramers-Kronig relation. P here is the principal part of the integral. Now, that's very nice. How is this all related to the wave function? Well, let's consider the logarithm of the wave function in the complex time domain. And let us ask if by knowing the amplitude, which we agreed is a measurable quantity, we can calculate the phase as in Kramers-Kronig relations. Now, this leads to other questions. One is, can we obtain the logarithm of the wave function if the logarithm of the wave function is analytic in any part of the complex time plane? If so, can we claim that it vanishes on the infinite semicircle? Well, let's try to answer those two questions by looking at a concrete example. So the most simple one is a propagating wave packet, a free propagating wave packet, I should say. And let's start with an initial condition, which is just a Gaussian. Okay, so you have just a Gaussian. It has a momentum, and everything is very nice. And this was solved analytically by Tomonaga in his book of 1966. And you get this form. The M of Tomonaga is just the physical M over H bar. Okay, so you have this solution. Now, let us insert an infinite potential barrier which does not allow any tunneling. So the free particle has a very high obstacle on its way. So what we really want is a wave function which is 0 for every x which is bigger or equal to 0, and this is, of course, includes the case where x is equal to 0. So by the method of images, we can construct such a wave function. This is the wave function. Just take x and minus x and subtract, and n is just a normalization. So this is a solution for x smaller than 0. And here it is. Okay, so the particle starts here, or the wave packet starts here, it goes here, and then it's reflected and goes back again. Now let me define this chi quantity, which would be 1 phi minus xt over c xt. So this is a kind of a multiplicative correction to the free wave function due to the potential barrier. Okay, so we have the free particle that does not know anything about the barrier. This is the correction. This is the normalization constant. And this is the total wave function written in this way. Now, you can calculate it explicitly, so you get something like that. Now, here are two questions. If we measure the amplitude of this quantity, can we calculate the phase? And more specifically, can we use the Kramer-Kronig type relation to calculate the phase from the amplitude? Okay, so this would be a kind of a Kramer-Kronig type relation in the time domain, which connect the logarithm of psi with the phase, the argument of psi, and of course vice versa, but we are more interested in that. Well, it depends. We should check if the function is analytic. Well, either in the upper complex plane or in the lower T plane. And since we use the function logarithm, we should avoid 0 as well as infinity, because we all know that the logarithm of 0 is infinity as well. And we should check if the logarithm of the function disappears at infinity. In other words, we require that the function be a unity at infinity, because the logarithm of unity is, of course, 0. Now, look at this expression and look at it for a complex T. Obviously, there are singularities in the upper T plane, so we better look at the lower T plane. Now, in the lower T plane, there are no singularities, but there are null points. So those are the null points. This is the equation for the null points. And we can calculate what T's solve this equation. So here are the solutions. Those are the null points. And this is the real part of the null point, and this is the imaginary part of the null point. Let us make some definitions. TR is just the time for a classical particle to reach the barrier from the where you start at point A. TD is the wave packet broadening typical time, and NRX is just this positive number over here. Now, in terms of those definitions, we have this real part and this imaginary part of the wave function, the null points of the wave function. Now let's see what we have. For n negative, we have many null points above the axis, but as we said, we have given up this upper part of the complex plane because we also have singularities. However, if for n positive, we may have either null points above or below the real axis. So the condition, as you can easily see, the condition for null points below the real axis is just for nr to be bigger than some integer. So we arrive at the necessary condition for that. And this is that nr is just bigger or equal to 1, which is the smaller integer. Now, the condition for log analyticity below the real axis is therefore that nr of x is equal to 1. Now, let us put back the definition of nr of x and the definition of p, and we arrive at this relation, which gives us the condition for log analyticity, which is x times p smaller than pi times h bar. Okay? So essentially, we can make this kind of trajectory when this function will be log-analytic below this real axis. However, the phase cannot be calculated in that way, and this is thus uncertain if x times p is bigger than h over 2, which is the log-analytic uncertainty relation. Now, you can compare it to another result from the 20s, Heisenberg uncertainty relation, which is of that form, sigma x, sigma p over h bar over 2. It looks similar, but this is a bit superficial. Why? Sigma x and sigma p are the standard deviation for the displacement and momentum of a particle. In the log-analytic case, what is considered is the distance from the potential barrier, which is x, absolute value, and the momentum of the classical particle, which is the average momentum of the quantum particle. So it's not a standard deviation, it's an average. The question now, is log analyticity below the axis enough to calculate the phase? The answer is no. We need to know how the function behaves on the infinite semicircle. However, by factoring the asymptotic behavior, the limitation can be overcome. So we just divide by the asymptotic behavior, and then we have a function which in the limit goes to 0. And if you do that, then you can show that one can calculate the phase from the amplitude. We have here a direct calculation and a calculation through the Kramers-Kronig relation. Let me conclude by saying that topology is important not only in space, but also in space-time. This is a point that Phil Boylan told us in the mid of the summer, but I would like to stress that this is true for real time, but also for complex time, in which the topological structure, which is null points and infinities, determine if a phase carries additional information to the amplitude or can be simply be derived from it. Provided that the log-analytic uncertainty relation is not satisfied, some aspect of the phase can be calculated from the amplitude, and notice that the entire phase cannot be derived, but only a kind of a partial phase, as I have shown. And I thank you very much for your attention.
Thank you very much. Do we have questions? Not? Okay, let's thank our speakers again, and let's reconvene at 3:30.